Hi, everybody. Welcome to the dark and scary part of the class, which is why I have the nighttime theme going in the little slideshow here. Not scary because of the exam. The exam went pretty good, actually, I think. I have the data here, and it looks like the average was around 76, 77%, which is great. I do want to remind everybody that the score that you are seeing on Canvas is incorrect currently. That's because Canvas thinks it's out of 83, and then it imported a percentage and applied that to 75. So whatever score you're seeing on your exam is wrong. I will go back and edit that at some point once I have enough time to do so. Other things to note about the exam. Your score is all you will get to see. You will not get to see your answers. You will not get to see the questions. You won't get to see any of that, just the score. The intent is that it's supposed to be treated kind of like a standardized exam. And that if I post the answers and the questions, then my exam can't be used again in the future by other instructors. And that's not something I'm willing to do. I'm not going to make the exam again. It took me like 7 hours to do. So, what your score is what you get. And it looks like most people did quite well. So I'm very happy with that. Other announcements to make. You can see all the announcements on the screen right now, but today we're doing Chapter 6. On Thursday, worksheet number 3 and quiz number 5 are both due. Make sure you get them both in by the deadline. Tomorrow, we would normally be going over lab worksheet number 4 according to the syllabus, but I've been working all week on the exams for both classes that I'm teaching, this one and another. And then after that, I had to move into doing lab worksheets for the other class, and I am still working on their worksheet, and I haven't even started this one. So, because that took way, way longer than I thought, I made the executive decision to postpone lab number 4 until next week. So instead of having the off week where we do nothing be next week, we're going to have it be this week. So there will be no Q&A tomorrow for the lab worksheet because there isn't one. And because you just had an exam and there's very little to go over, I'm going to cancel that Q&A session too. So there will be no stream at all tomorrow. You get a night off. And if you have any questions about anything, you can always email me. So make sure to use that resource as you need it. All right, and I'll send out another announcement for that tomorrow night, just to remind you that, hey, we're not going to do anything, so enjoy the night off. Tonight, we're going to do Chapter 6. Chapter 6 is probably what students tell me the hardest math chapter in this class. And if you can make it here, you can make it anywhere in Chem 121, is my opinion. We're going to be going back to a lot of the dimensional analysis conversions. So remember Maya the cat, how we had to calculate medicine for her? We're going to do that on a whole different level. And this will get progressively more complex as we go. So it's very important that not only are you following along with what we are doing on screen and writing your own notes and doing all that, but that you ask questions if you get confused. Because we're going to be doing a lot of dimensional analysis. We're going to be doing a lot of those little maps where we link one unit to the other. We're going to be doing the same pattern over and over and over and over and over again. You got to do it my way. You got to make sure that you get into the rhythm and the habit of doing it in the way that I'm showing you so that you have that skill set ready for when you take quiz number 6, which will probably be next week some point, and also exam number 2 and the final, because these questions will keep coming around. So let's talk about this new unit. I don't remember if we mentioned the mole very early on. It's the unit of counting. But we're going to introduce it in this chapter, and we're going to use it to do calculations involving stuff that we would use in the laboratory. So the first thing I want to comment on is the periodic table. In Chapter 3, which seems so long ago, we determined the atomic mass of any element in AMU, and that was the number at the bottom of the periodic table. So for example, if I look at oxygen, on the periodic table for oxygen, it has the oxygen symbol, and then underneath it, it says this. And this number right here was its mass in atomic mass units. Now, if I wanted to do this for a formula, so like H2O, for example, how would I figure out what H2O weighs in atomic mass units? And the way that you do that is you just simply add all of the numbers together on the periodic table. So it's like shopping. If I wanted to go to the periodic table store and I wanted to buy 2 H's and an O, the costs would be shown as the mass number, and I would pay however many AMU all of those add together to be. Now, since we're doing addition, you got to worry about sig figs again. So what that means is that your answer is going to depend on what periodic table you're using. Most periodic tables have at least 2 decimal points. And so if your numbers go down to the second decimal point, your answer that you report at the end should also have 2 decimal points. Remember that we care about decimal points for addition, because that's what we're doing here. So as an example, here is tin to fluoride. And if I wanted to calculate the atomic mass or the formula mass of these substances, I would look them up on the periodic table. So I'd look for tin, and I see that's 118.71. And I'd look up fluorine, and I see that it's 19.00, and I have 2 of those. So I'd punch this all in my calculator. I'd just take 118.71, and then add it to 19 times 2. And when I punch that in, I get 156.71. So the mass of this compound would be that much, 156.71 atomic mass units, or mu. And so you could do this for any compound that you need to. You just add all the numbers together off the periodic table. Simple as that. All right, so I'm going to give this to you for an example. You'll need to get a periodic table. Remember, P-Table is a good website for one. If you don't have it bookmarked already, you can Google it. And I want you to tell me, how much does this compound weigh in AMU? And when you get your answer, type it in the chat. So I'll give you a few minutes to do that. All right, we have some answers coming in. Keep typing them in the chat when you get it. I'm going to give everybody a second to do this. I actually don't know the answer yet. I have to do it on paper. And remember, your sig figs will depend on what periodic table you're using. So you might get a different number of sig figs from someone else, and that's okay. We're not super invested on sig figs for this problem. What we care about is just getting the right ballpark answer. And I see a bunch of answers, so let's go to the sample problem. Viewer. And we'll... Oops, hold on. There we go. Alright, so I can't write up there because you can't see it. Alright, so I've got NH2CO. And so if I split this into how many atoms there are 2 N's, there's 4 H's, a C, and an O. And I get the 2 and the 4 because I have to multiply this 2 in from the parentheses. Alright, so I'm just grabbing these numbers off the periodic table that I have handy here. Oops, that was supposed to be a U. Alright, and so there we go. That's what I have for those numbers. I didn't grab my calculator. I gotta do that. So when I punch this all into the calculator, I get this. So when I add it all together, I get 60.06 AMU. And I'm rounding to the hundredths place because all these numbers go to the hundredths place. This one goes to the thousandths place, but I don't have that in the other numbers. Now, if you got a periodic table that had all thousandths values, so you had like 14.011 or 007 or whatever, then you could keep the thousandths place, and that's fine. But for this exercise, we're just trying to get to the general ballpark of the answer. Oops, that wasn't the answer, so that was just... Oops. Not on the screen. There we go. Alright, so that's how you do that. I have more examples for you to try if you want to. I'm not sure if we need to spend time doing basic addition, but if you'd like to do these, I can give you a few minutes to do them. What do y'all say? Do you want to keep going? Do you want to practice this? What is your decision? And the reason I say this is because we're going to be doing this process a lot today. We're going to just be adding all these numbers up. I'm going to just assume that you know how to do it. We gotta move on. Okay. Is anyone else okay with anyone else not okay with moving on? Sounds like everyone's good. All right, so we're gonna keep going. All right. Let's talk about moles. Now, a mole is just a collection of things that we've assigned a number to. It's kind of like... Oh, just a second. Excuse me. It's kind of like some terminology that we use like this. So, for example, if I have a dozen of donuts... A dozen of donuts. Nobody says that. If I have a dozen donuts, the word dozen implies this many. And we'll say 1 dozen donuts is equal to 12 donuts. If I had a couple of, I don't know, calculators, how many is in a couple? Well, it's 2. Well, if I had a mole of something, and we'll say like a mole of beach balls, we'll say, then the amount of beach balls I would have would be this many. That is an insane number of beach balls. You could literally make a planet-sized object out of beach balls if you had that many. So a mole is just a collection of things. And so we use that to count in groups of 6.022 times 10 to the 23. And so that should appear on the screen here. Now, where does this number come from? Where does the number 6.022 times 10 to the 23 come from? And that should actually appear down there. That's what I want. Well, it turns out that we got this number by taking a sample of carbon-12 and saying, okay, we're going to use this as our counting measure. And in 12 grams of carbon-12, it was calculated that there were this many atoms of carbon. And so that's just our reference. Somebody said, we're going to pick carbon. That's fine. How much carbon should we use? Let's use its mass number. And because of that definition, what this means is that a mole of things is related to its atomic mass. And that atomic mass is related to its count. And the count will always be 6.022 times 10 to the 23 objects for 1 mole. Now, with these numbers, it's important to note, this number is exact, which means it has an infinite sig figs. But this number is inexact. Because there's no way that we can get all the way down to the 23rd digit and know it exactly. So from this information, we can now construct relationships between how many objects something has, how many moles something has, and how much its mass is in AMU. But it'd be really nice if we could do that with just, like, say, grams or something, and that's actually what we're going to do in a second. You're going to hear me refer to this name a lot during today. The number 6.022 times 10 to the 23 is called Avogadro's number. Avogadro was a chemist in, I want to say 1900s. I don't really remember when. It's not important. But he did lots of work with gases, and he was the one who pioneered all of the work that eventually came up with this value for the amount of objects in 1 mole. And you're going to use this number so much that you're going to have it memorized. Now, it turns out that the measurements that we have made to get those atomic mass numbers on the periodic table have been made with the mole in mind. And it turns out that we have devised this system to represent the number of grams in 1 mole. So if you look on the periodic table, all of those mass numbers that we said were in AMU, we're going to get rid of AMU, and we're never going to talk about it again because it's not really useful to us. But what is useful is to say, oh, okay, that number in AMU is the number of grams per mole. And so on the periodic table, we have iron. Iron is 55.845 as its mass at the bottom of the box. That means that 1 mole of iron weighs that many grams. And in that many grams of iron, you would have 6.022 times 10 to the 23 atoms of iron. And that gives us a bunch of relationships. Of these 3 relationships, we only really need these first 2, but the third one is true. I'm going to highlight the important ones that you should understand. Because this allows us to turn grams into moles, and this learns us to turn atoms into moles. And this last one exists but is not super useful. For a lot of our calculations, we're going to be asking ourselves, what is this quantity and what is the answer in this value? Excuse me. Many, many times we're going to need to figure out how many moles are present so that we can use that in a calculation. So what we're going to do is we're going to do a bunch of calculations similar to those that we saw in Chapter 2, but using these new conversion factors. Okay? So let's do some examples here, and we'll start with this example here. What is the mass of 2.6 moles of sulfur? So let me get this. Boop. All right, so let's write down what we know for our units. First of all, we'll make a little chart here. So I know how many moles of sulfur I have. And what I want to do is I want to figure out the mass of sulfur, which is grams. And I need to relate these two by making a conversion that relates moles of sulfur to grams of sulfur. And so what I want you to do is type in the relationship in the chat between these two substances based on what we just discussed. So find out how many grams there are in a mole of sulfur. And I'll give you a hint. You got to look somewhere for it. How many grams are in a mole of sulfur? So you can use Wolfram. I would use p-table, personally. Because you're going to need to look at the periodic table for this. .06 is the right number. And there it is. But yeah, you can look on Wolfram Alpha. That works too. All right, so now we got to put that number somewhere in here. So we know that in 1 mole of sulfur, there are 32.06 grams of sulfur. And that's according to the periodic table that we have in front of us. Or Wolfram Alpha, depending on what you used. Okay, now that I know this, I can set up my relationships and do the calculations. So we'll write down the number that we got, 2.6 moles of sulfur. And let's do dimensional analysis. So I don't want this unit. I want to turn it into grams. So I'm going to take this unit and put it down here so that it matches. We all remember this, right, from Chapter 2? And I'm going to turn moles into grams because that's my linked unit. And then that's the target, so I'm going to just hit equal. And I just got to put the numbers in where they go. So moles was 1, and grams was 32.06. And then you punch it in the calculator. 83.356. And then the last thing we got to do is consider sig figs. How many sig figs should my answer have? Well, this number has 2 sig figs. This is exact. And this has 4 sig figs. The lowest one of those is 2, so my answer should only have 2 sig figs. So I would report it as this. And that's how we do basic mole calculations. Any questions, let me know in the chat. Oh, I spun the thing the wrong way. All right. On my slide, I provided exactly the same thing that we just did. I had fewer sig figs when I wrote this problem, apparently. That's okay. All right. Let's do another one. All right, does that fit? Almost. There we go. How many atoms are in 49.1 grams of sulfur? So I gotta scroll this down. All right, so this time I have grams of sulfur, and I need to figure out how many atoms of sulfur there are. So what I need to do is I need to link the units. Now, I had that relationship before that I told you wasn't super useful, because what's more useful instead is to go through moles, because it's a little more practice doing this, but also we're going to be converting stuff to moles all the time anyway later. So we might as well just get in the habit of doing it now. So now that I've linked my units together, let's make some relationships. What is the relationship between grams of sulfur and moles of sulfur? And you might just be saying, well, duh, it's the same thing we just did before. It was 1 mole is 32.06 grams of sulfur, and that's right. Now what's the relationship between moles and atoms? Type that one into the chat. What's the relationship between atoms and moles? How many atoms are in a mole? I'll give you a hint. It's that number that you haven't memorized yet. Yeah, that number. There you go. Whenever you see atoms and moles, you're always just going to write the same number, because in a mole of anything, there are Avogadro's number. I gotta make that dot bigger there. There are Avogadro's number of atoms in a mole. Now, later on, I'm going to change the word atoms with particles, because I could be counting ions, I could be counting molecules, I could be counting formula units, I could be counting beach balls, I could count anything with it. But for this problem, we're going to work in atoms, because that's what it's asking us to do. So we now have our relationships. Let's take our value that we know, which is 49.1 grams of sulfur. And what we're going to do with that is we're going to convert from grams to moles, because that's the connecting unit. So this goes down here because I don't want it. We'll put the linked unit on top. That's not the unit I want for my answer, so I got to turn it from moles into atoms here. This is the unit that I want, so when I hit enter, and I'm going to put it over here, we'll get our answer. We just now need to put in the numbers. So grams to moles was this relationship right here, 32.06 grams per 1 mole. Very important, make sure you're putting the numbers in the right spot. And then there are 6.022 times 10 to the 23 atoms in a mole. And we'll punch all that in the calculator. And the number it spits out for me is 9.222713, whatever. I only get to keep 3 of these anyway. Times 10 to the 23 atoms of sulfur. All right. Hopefully that made sense. Let me know if you have any questions on how to do that. On the slides, I show the way to do it with just one conversion. And you get the same answer regardless. All right. This problem needs to do this. All right, last problem we have for the sulfur examples. How many moles are in 71.25 grams of sulfur? So let's give that a try here. I got to get back to here, delete. So I ran out of space. We're going to go back to the top. All right, and so we're going to go from, we're starting with grams of sulfur, because that's the problem is asking. We have moles of sulfur as our desired unit at the end. I can connect one to the other because I know the relationship between grams of sulfur and moles of sulfur. And 1 mole has 32.06 grams of sulfur in it. Will the answer always be the calculated number times 10 to the 23? It won't, actually. So if you got a number that was like 14 times 10 to the 23, your calculator will move the decimal point, and it will call it 1.4 times 10 to the 24. So depending on what you are working with, don't always expect there to be a 23 at the end there. But for Avogadro's number, whenever you write Avogadro's number, that will always be a times 10 to the 23. All right, we got our unit set up. Let's type in, or not type in, but write down the number. I'm going to use grams to get canceled out on the bottom. We'll write the linked unit over here. That's the unit I want for my answer. So let's run the numbers. In a mole, there are 32.065 grams of sulfur. I added an extra number here. I know what the next number is, so I keep wanting to add it. And if I divide those two numbers, I will get the number of moles. I got 2.222 moles of sulfur. All twos. Oops, all twos. Whenever you're doing these problems, make sure that you are noting the following things to just check your work. So the number of moles or grams should be a reasonable size number. And whenever you're doing this calculation and you're trying to get the number of atoms, your answer should be ginormous. Okay? So in other words, you should not be getting a 10 times 10 to the 20th answer when calculating the number of moles or grams. Because something that is times 10 to the 20 grams would be like the mass of the moon. That would be ginormous. For a number of atoms, though, there are a ginormous quantity of atoms in a very small amount. For example, if you hold up like a shot glass of water, that's about a mole. And that would have 6.022 times 10 to the 23 molecules of water in it. But the water inside is not very much. It's only like 20 milliliters. All right, so we have done 3 examples. So what I want you to do is to try the following problems on your own. And these I do want you to do. So I'm going to give you a helium balloon. The balloon has 1.7 moles of helium in there. How many grams is that? How many sodium atoms are in a 34-gram sample of sodium? And then finally, how many moles of lead are in this ingot that weighs 805 grams? So calculate those 3 problems. Make sure that you type your answer in the chat when you are done. Compare your answers with each other, and we'll go over the answers in just a moment. Alright. Hopefully everybody's almost finished up. There's a cat here that wants to say hi. It's not Maya, it's the other one. Come on up, Kresnik. Come on up. You want to meow for everybody? Meow. He's quiet, except when he doesn't want to be. Where'd you go? There you are. Alright. From the sound of it, it sounds like most people are getting there. So let's go over the answers here. So for this first one, 1 mole or 1.7 moles of helium. We start with the quantity of moles of helium. We want to turn that into a mass. So I want to use the relationship moles to grams. And what does my periodic table say here? I can't see it from there. 4.002. 6. Ah, what just hit my foot? Oh, it was my cat. Alright, so we have that relationship here. My cat is being a pest. He always is. We'll turn moles into grams, just like we did before. 1 mole is 4.0026 grams of helium. If you didn't have that many sig figs on your mass, that's fine, because it's going to disappear with my 1.7 anyway. And I got 6.8 grams of helium. All right, let's go on to the next one. Oh, I gotta do this in this part. There we go. There you go. We're gonna do the same thing, except we're gonna go from grams to atoms for this problem. So I need to scroll this down a little bit. We're gonna start with grams of sodium. We're gonna turn that into atoms of sodium, which is our goal. And whenever we go from one of these to the other, I like to go through the middle, which is moles. And then my relationships for grams and moles are, let's see, sodium is 22.990. And that's a mole of sodium. And then in a mole of sodium, there are always Avogadro's number atoms of it. So we'll come up here. We're going to start with 34 grams of sodium. We'll do the dimensional analysis just like we did before. We'll turn grams of sodium into moles of sodium. That's not the unit I want, so I'll do moles of sodium to atoms of sodium. And that will give me my answer once I plug in all the numbers. So grams to moles, 22.990 per mole. And then Avogadro's number per mole. And for this one, I got 8.91 times 10 to the 23 atoms of sodium. Don't forget that times 10 to the 23. That's important. Oh, you might have heard him now. Hi. Meow. He just, like, licked my elbow, and I was like, ah! And then he meowed at me. Meow. He really wants to jump up on my lap, but I have a tablet in my lap. I can't help you. Alright. I'm kind of out of space again, so I gotta erase again. Boop. Oh, that's not what was supposed to happen. I don't know why it turned red. Surprise, red! Oh, I gotta put the problem on here, too. What, are you confused that you hear me talking to random people? I do this every other day. Not just to my students. Oh, now he's gone. Alright, how many moles of lead are in an ingot weighing 805 grams? We want to turn grams to moles. That's pretty straightforward because the mass of this is 207.2 grams of lead per mole of lead. And so let's do the calculation. I have 805 grams of lead. I'm going to put the units down here so they cancel. Not platinum. There we go. We're going to turn that into moles. And then we'll just write in the relationship because that's all we need. 207.2. Let's just try that number again. And so we get 805, 207.2. I got 3.88 moles of lead. I love platinum. I don't know why. I'd much rather have platinum than lead, I guess. Alright, and there you go. Oh, it should be 3.89. That's okay. As long as you're close. And there you go. That's how we do those simple calculations for converting grams to moles to particles. When we come back from the break, we're going to take a break now, because this is a good stopping point. When we come back from our break, what we're going to do is we are going to expand on this idea and start looking at chemical formulas and try and figure out different quantities within those molecules. So I might give you, like, here is a mole of sugar. How many moles of oxygen atoms are in there given the formula? And so that's the sort of calculation we're going to do in a second. There's the homework practice. Leave that on the board for a second. The cat's going to stare at me, aren't you? Meow. Yeah, they want to hear you. Say hi. He's shy. Huh, buddy? Alright, I'm going to take care of the cat. We'll put the title card back up. Let's see here. Boop. Boop. Oh, I gotta do this, though. There we go. So I'll start the timer. I'll start the music. And I'll see you in about 10 minutes. Oh, so close. I'm not sure I can land right on 10 exactly, but that's okay. Boop. Oops. What did I just do? Boop. Boop. There we go. All right, we're back. Hope you enjoyed your break. Now what we are going to do is we're going to do the same calculations that we did as before, but we're going to add one extra step to it. And that extra step is going to be a little like a comparison step. And that's going to require me to do a little bit of algebra for you to show how that works. And so let me set up this right here. And we're going to go to this page right here. Now, if I give you a molecule, the numbers in the molecule tell me how many of each atom or element there is inside that molecule. So, for example, in this molecule right here, P2O5, excuse me, there are 2 phosphorus atoms and 5 oxygen atoms in one molecule. And what that means is that if I... Oops, that's not useful to anybody. What that means is that I could write a sentence like this. So in one molecule P2O5, there are 2 phosphorus and 5 oxygen atoms. So in one molecule P2O5, there are 5 phosphorus... Oops, not 5 phosphorus, sorry. Looking at the wrong one. There are 2 phosphorus atoms. That's not the letter for atoms. And there's also 5 oxygen atoms. And so this equality makes sense for the molecule that we've written on the board, and only this molecule on the board. If I had a different molecule, I have to write a different equality. So basically what we've done is we've translated that sentence into math. And what I'm going to do for this first part is I'm going to ignore this part over here. This is just extra. We're going to just work with one part of the equality because I could potentially ignore this one instead and then use the other one. But what I'm going to do is I'm going to take this equation right here and I'm going to move it down here. One molecule P2O5 equals 2 phosphorus atoms. And you might say, well, where did the oxygen go? And it's still here. It's just that we're not using that part of the expression. Because this is how equalities work. If x equals 5 and y equals 5, then x equals y. And I could say x equals y equals 5, but I could work with them all independently. And so that's what I'm going to do here. I'm going to take this expression right here, and I'm going to times it by a mole. Because we've been working with moles today. So let's use moles as our unit because we can convert moles to grams and stuff like that. So if I had something in moles, that would be a useful unit. Well, 1 mole times a molecule is a mole of molecules. So I could say, oops, I could do that apparently. That's not what I meant to do. What am I doing? Oh, I'm not zooming out, that's why. I accidentally zoomed in. Sorry about that. So 1 mole times a molecule would be a mole of molecules, or in other words, 1 mole of P2O5. And 2 atoms times a mole would be 2 moles of atoms, or in other words, 2 moles of phosphorus. And so what we've done here is we have created a relationship between the coefficients in our molecule and the numbers that come in front of these statements. Now, I could do the same thing where I used 1 molecule P2O5 and 5 oxygen atoms. I could write the same equation. By following the same sort of rule. And so both of these expressions are valid for this molecule. Now you might ask yourself, well, why do we care about these expressions? Like, why would we spend this time creating them? And the answer is because now I can ask questions such as, if I give you a mole of P2O5, how many moles of oxygen are in that sample? And it doesn't have to be 1 mole. It could be 20 moles or 7.4 or whatever. And then I could say things like, if I gave you 10 grams of P2O5, how many grams of oxygen are in there? Because we know how to turn grams to moles. And so that's what the focus of this section is going to be. So let's use these equations that we just created and answer some questions here. For instance, how many moles of oxygen are in 2.5 moles of P2O5? I should have just really done this to that. Because now what we can do is we can use one of these expressions that we just created and figure out how many moles of that thing are in a mole of P2O5. So I'm going to take this as my unit. So this is the units that I'm starting with, because that's the one I have a number. And I want to figure out how many moles of oxygen are in there. And I know that for every mole of P2O5, I have some number of moles of oxygen. And that's just this relationship right here. So now if I do the dimensional analysis, how many moles of P2O5 do I have? I have 2.50. I could then do this, moles of P2O5, moles of oxygen. Cancel those out. And I know that there are 5 O's per P2O5. And so there must be 12.5 moles of oxygen in 2.5 moles of P2O5. And so if you were thinking before when you saw the problem, well, duh, you just times it by 5. Yeah, you do multiply by 5, but that's how the units work out. Now, if I didn't want this answer to be in moles, what I could do is I could then turn it into grams of oxygen, because I know that how many grams there are per mole. And if I didn't start with moles of P2O5, maybe I started with grams of P2O5, I could turn that into moles. And you can see how this relationship starts building on itself. And we just make longer and longer and longer calculations. This is about as long as we're going to go, but you could theoretically go as long as you want. As long as your units work out, and as long as the dimensional analysis cancels the units that you don't want and leaves the ones you do. So let's try some more complicated examples using this molecule, C3H6O3. How many moles of carbon are in 1.2 moles of C3H6O3? So what I want you to do is write out the dimensional analysis and tell me how many carbon moles there are in this sample of molecules. Okay, we'll go over the answer in just a bit. So I'll give you 2 or 3 minutes to set this up and give it a try. I'm sitting here talking to myself, and I realized, oh, I'd never unmuted it. Oops. I saw an answer in the chat, and that answer is correct. Let's show how you get that answer on the... Oh, I gotta click over here, too. Oops. I'm a mess. There you go. Alright, so first we want to relate the moles of this molecule to the moles of carbon. And I know that for every mole of this big molecule I have, I must have this many moles of carbon, because that's the coefficient. So now I will take my starting value, oops, and then we'll set up the dimensional analysis here. These cancel out. And there are 3 carbons per mole of the big thing. And so I just multiply the numbers together. And there you go. Now let's make the problem a little more complicated. How many moles of oxygen atoms are in this many grams of C3H6O3? So now what you have to do is you don't get the moles to start, you get grams, so turn it into moles. And then from there, you can answer the question. So I'm going to let you try this for a little bit, and we'll go over the answer together in just a second. Oh no, there's now a cat on my lap. So I'll let you keep working. Type in your answer when you get it. And I'll have to shoo the cat away to solve the problem because I can't actually write like this. How are we doing? I'm stuck with a cat in my lap. Alright, I gotta pick you up. I gotta solve a problem. Yeah, I gotta do the math. Oh, there you go. He's on the floor now, and he's upset with me. Why did you put me on the floor? I thought we were having such fun. Oh, I worked in the middle of the problem here. I don't know why I did that. Alright, so let's go over how to do this. First, by writing out the unit map, and then hopefully people will catch on to the step that they missed if they are stuck. So I know the number of grams that I have of this molecule. And this problem is asking me to get to moles of oxygen. Now, if I knew the number of moles of the molecule, then this step would be really easy, wouldn't it? Because you just say, in a mole of the big thing, there are 3 moles of the small thing, because there's a 3 there. Do you know the way to get from this one to this one? And unfortunately, your answer should not have Avogadro's number in it, because that is unfortunately too big. How do I do this step here? I'll give you a hint. We just did it in the previous section. Oh, goodness. I just knocked things over. Okay, at least I didn't break my little knick-knack. That would have made me really sad. What did I spill soda on? Not my keyboard, not the tablet. That's really all that matters. I'll let you try that while I clean up. Sorry about that. I'll be right back. Alright, sorry about that. I had to clean up 7-Up everywhere. Oh, I just found more of it. Darn it. Where did that... Oh, crap. Sorry, I'll be right back. Alright, let's go over the answer before I find more stuff that I have to clean up. I can't blame the cat for that. The cat had left. I just went to grab my mug, and I hit a little statue that I have on my desk, and it fell over into it. Into the mug. Whoops. Okay. They're both fine, though, which is good because I really like the statue. Alright, so I need a relationship between grams and moles, and the way you do that is you grab it from the periodic table and find the formula mass. So I'm going to get 3 C's plus 6 H's plus 3 O's. When I type that in my calculator, oops, I gotta erase this. What I get is there are 90.7077 grams of C3H6O3 in 1 mole of that. I need to give myself more space. I'm just cramming this over in the side here. And so again, that was the formula mass for the compound, which you grab off the periodic table. And now that I've done that, I have a link from grams of this substance all the way down to moles of oxygen, so I can solve the problem now. And I'll do this a little smaller so that I can fit it all in here. I guess what I could do is I could do this. Now I can't see it. Alright, I guess we'll just go like this. So let's set up the units first. So those will cancel out with these. That's going to turn grams into moles, because those are my linked units. And then I'll turn moles of C3H6 into moles of O3. Oops, sorry, moles of C3H6O3 into moles of O is what I meant to say. And that will give me my answer in moles of O, which is what I want. So now let's run the numbers. There is 90.077 grams of this in a mole. And then in a mole of the molecule, there are 3 moles of oxygen. We'll type it all in to the calculator. That's not what I meant to type. I got 4.795, which for 3 sig figs would be 4.80 moles of oxygen. Ah, I messed up. There we go. There we go. All right. So now for this last problem. Well, actually, I don't want to do this because this is just what we were doing for the previous example. So I'll go back here. I'm going to leave this as an exercise for you, because the next thing that we're going to do is we're going to do this for more complex problems, such as medicines and stuff like that. And we're going to do a few of those, and then we'll call it a day. Oh, there's the homework practice. Yeah, we'll just do... There you go. Oh, man, I got 7-Up on my phone. I have to wash my phone case off. That's okay. All right, so let's do some of these problems for more practice, because more practice is good. These slides just show you how you can convert one thing to another, which we've been doing all along. This right here, where it says particles, this is how many atoms of something we have. But it could also be how many molecules we have of something, or formula units, or whatever. What this box really is a count. If you are counting something, you're going to try and navigate to this box. We know what moles is and we know what grams is, and these relationships in the middle here represent the factor that connects the two. So either we're going to have Avogadro's number connecting us to moles, or we're going to have the molar mass connecting the moles. And this is for one specific substance. Now, if you want to go between substances, you could use the trick that we just used to use the formula subscripts to turn moles of something, like A is the big thing, and B is the part of that. Now, because I can turn both sides of the moles into grams or particles, what I'm going to do is make this one giant chart that if you use this, it's basically a blueprint on where you need to go. So this chart will help you map out your units like we've been doing all along, but it's already there for you. So if you have it during a quiz or an exam and you're like, okay, he gave me grams, and I'm going to turn that into moles, and then I'm going to turn that into moles of the part, and I'm going to turn that into atoms of the part, or whatever. So now you can use this as a guide to link the units that you want from one spot to another. And as we do these problems, I'm going to put them, the little guide in the corner to help us. Now, what's important is that you're going to have to distinguish between when you need to use this bridge and when you don't. For instance, the problems that we've been doing so far, in this section anyway, before the break, we just turned between grams and particles and moles. And in this section today, or after the break, we did this part where we crossed this bridge. We turned moles of something into moles of something else. What you'll need to do is you'll need to look at the problem that's being asked and tell yourself, is the thing that I have a given for, is it the same substance as the thing that I'm being asked to solve for? And if the answer is yes, I am solving for the same thing that I started with, and that's the wrong color, but that's all right, then you're not going to use this bridge at all. You're just going to convert along the same path like we've been doing. But if you are given two things and they are different, then you do need to cross the bridge. If I ask you, here's how many grams of vitamin C you have, how many grams of oxygen are there? Oxygen and vitamin C are different, so we're going to have to turn from moles of something to moles of something else. So I'm going to do this first one as a practice problem to show you how to do it. If I can find the right thing. All right. I didn't actually mean to leave this with all of the highlighter on it, so let's get rid of that. All right, and let's do our practice problem here. So sample of vitamin C weighs 0.250 grams. How many vitamin C molecules are there? What are you starting with? And what are you ending with? I'll give you a second to think about that, and then try and link the units together, and then we'll do the problem once I have this set up here. That's good enough, okay. So you should have realized, oh, these are the same thing, so I'm going to link grams to moles, moles to molecules, and then I'll be set. And now you just got to write the relationships between them. So how many grams of vitamin C are in a mole of vitamin C? Where would you find that information? And then in a mole of vitamin C, how many molecules are there? Where would you find that information? And it's all about just getting the right numbers and putting them in the right spot. That's the trick here. I put the wrong molecule into the Wolfram alpha. So I calculated, well, I didn't calculate, the system calculated, that there were 176.12 grams of vitamin C per mole. And again, that's just the formula mass, so we just calculate that from the periodic table. And then for a mole of vitamin C, how many molecules are there? Well, how many molecules are there in any mole? There are Avogadro's number of them. So now that we know all the relationships, I can now start the problem. I gave you 250 milligrams of vitamin C. And I want to convert that to the linked unit, which is moles of vitamin C. So grams of vitamin C down here to cancel. And I want to convert that to the linked unit. And we're all set. So now we just plug in our numbers. 1 mole of vitamin C was 176.12 grams. And 1 mole of vitamin C was Avogadro's number of molecules of vitamin C. And so we punched it in the calculator. I gotta find my calculator because I put it away when I spilled everything. And I got 8.58 times 10 to the 20 molecules of vitamin C. And so that's probably the first example that we've had where it didn't have a 23 on there. And this is possible, so it all just depends on what numbers I give you. You could get any number really at all. Now, if you go back to the slide here, if you want to use this chart instead, what you could say was that, oh, okay, I was given a quantity of vitamin C that weighs 0.250. That's a mass. So I would be starting here on the... Oh, that's not a good color. I chose the complementary color. What am I doing? Let's do orange. That'll show up. I know color theory. I should be able to... Oh, that doesn't show up at all. Whatever. It's this one, okay? There we go. So I should start there, and then I am asked how many molecules are there. So I should end here. So if you indicate those, then each step that you go is going to be a conversion. So you're going to turn grams to moles first, then you're going to turn moles into particles second. And that's exactly what we did on our problem, which you can see again here. We turn grams into moles first, and then we turn moles into molecules second. So whichever way helps you set up the problem, do that way. And then do the dimensional analysis like I've showed you. What you want to do is you want to do it the same way every time so that you'll do it correctly. There's our answer. Let's give you another one. I'm going to give you caffeine because it seems like everyone's asleep right now. There's nobody chatting in the chat. So I'm going to give you 0.1 grams of caffeine. That's a lot of caffeine, by the way. How many of those grams are nitrogen? So the first thing you want to do is you want to identify what your starting unit is, which one has the number, What's your target unit? What are you trying to solve for? And then link the units together, and you can either use the chart shown on the... It's not updating. Uh-oh. Oh, is the chat not updating? Oh, that's weird. Yeah, I just saw that in the chat window. For the previous problem. I don't know why you would get that number if I can't see your keystrokes or what you've entered in the calculator. But you should do 0.25 divided by 176.12, and then times 6.1022 times 10 to the 23. Make sure you you hit enter between each of those. Just to be sure that you're doing it in the right order. All right, so what are we starting with on this problem here? I have a sample caffeine. Here's my caffeine. And it weighs some sort of mass. That's a mass, so I'm going to start here. And then the next part of the problem asks you, how many grams of nitrogen? That's also a mass, but nitrogen is not the same as caffeine, so that means I need to go here. And in order to do this calculation, I would need to turn grams to moles, grams of caffeine to moles of caffeine specifically, then moles of caffeine into moles of nitrogen, and moles of nitrogen into grams of nitrogen. So what I want you to do is, using that blueprint, I want you to solve the problem and tell me how many grams of nitrogen there are in this sample of caffeine. And as a hint, you should get a number that is smaller than 0.1, because you can't have more nitrogen than the total sample, right? So do the calculation and tell me what you get for your answer. How are we doing? I have a cat on my lap again. He just won't leave me alone today. I'm gonna trip over my headset, Mike. Don't do that. I gotta put you down. Oh, I didn't hit mute. Damn it. How are we doing on this problem? Should we go over the answer, or do we need more time? Let's go over... Sorry, I just clicked on this and it told me that there was, like, an issue. But I think the issue is that I'm not talking and it's just streaming me being silent. The audio stream's current bitrate is 0. So let's go over the answer. And I have a sample of caffeine, so I know the mass of the caffeine. So I know grams of caffeine. I just got your message. Let me continue with the problem here. So grams of nitrogen. So what I need to do with this is I need to turn this into moles of caffeine. And then moles of nitrogen. And then grams of nitrogen. I'm not sure what's with YouTube today. It could just be a little laggy. So moles of caffeine and moles of nitrogen are pretty straightforward. So in a mole of caffeine, oops, which is C8H10 and 4O2, how many moles of nitrogen are there? And you should say, oh, okay, well, the formula coefficient tells me that that is 4. Kresnik, get down. My cat's now climbing on everything. He's being a cat. Down here for moles of nitrogen to grams of nitrogen, we use the number off the periodic table, which is this. And then for caffeine to... Sorry. And for caffeine to moles, I need to look up the molar mass of that real quick. And I got 194.19 grams per mole of that. So... And so those are our relationships for this problem. So now what I can do is I can start drawing lines all over the place, apparently. I can start with my 0.10 grams of caffeine. I can then convert grams of caffeine into moles of caffeine, because that's my linked unit right here. I could then convert moles of caffeine into moles of nitrogen, because that's my linked unit that connects these guys. And then, so I ran out of space, we'll put moles of nitrogen on the bottom and turn it into grams of nitrogen, because that's my linked unit here. Now I just got to fill in the numbers. How many grams are there per mole of caffeine? 194.19 per mole. In 1 mole of caffeine, there were 4 moles of nitrogen. And then finally, in 1 mole of nitrogen, there are 14.01 grams of nitrogen. So I times it all together, 0.1 times 4 times 14.01 divided by 194.19. And when I do the rounding, I get this 0.029. That's just, there's just not enough space here. .029 grams of nitrogen. All right. Are there any questions on how we did that problem? That's all we have time for today. Oh my god, now I have another cat in here. Get out of here. I just fed them. I don't know why they're bugging me. All right, so that is all the time that we have for today. There are more of these problems that I would like you to try. And there we go. So there's the answer. I do have this one with adrenaline, which you can try. Here's the answer to that problem if you are curious about that. But do try and do this calculation. And then I have more of these on this next slide. I'm going to skip this problem right here when we come back on Thursday. But on Thursday, we're going to start here, and I'm going to go over the answers. So please try to do these problems. I'll put the homework practice on the board here so that you are proficient with them, because we're going to use this strategy again when we're on Thursday doing calculations with chemical reactions. And we're also going to talk about how to balance a chemical reaction, which means that we're finally going to actually start doing chemistry and building reactions at that time. How did I find the grams of caffeine? So I added all the formula masses together off the periodic table. So C is 12.011, and I had however many of them. H is 1.0079, I had however many. N was 14.007, and then O was 15.999. So it's like the thing that we did at the very start of the period today. All right, any other questions before we call it a day? All right, I do want to remind everybody that this is one of the hardest chapters. So if you are feeling stuck, that's okay. Don't give up. Make sure that you are going back and reviewing the lecture slides and the lecture video, and just watch me do it over and over and over again. Just because you've seen it once doesn't mean that it's immediately garbage and you don't have to watch it ever again. Feel free to review it as much as you need. Send me an email if you have any questions about what you need to do. Remember the due dates on the stuff that is due on Thursday, so worksheet number 3 and quiz number 5. And again, no lab lecture or Q&A tomorrow because I just don't have your lab report done. I'm not going to be able to get it done. I'm almost done with the first one now for the other class, so I got to get started on yours. But I'll definitely have it for next week. Thanks for watching. Have a wonderful evening. Stay safe, stay healthy, stay at home.